Hello, my name is Tyler Kunze, and I'm a senior here at UW Green Bay. I conducted an independent research study with Dr. John Luchai, and we created a regional groundwater isoscape for both deuterium and oxygen-18 isotopes in the shallow Silurian aquifer in northeastern Wisconsin. We collected our samples from the shallow Silurian dolomite aquifer, which is the purple band on the lower picture along the eastern coast of Wisconsin up through Door County. It's also circled here on the top right in the image on the right. It is fractured and karsted, which means there's conduit flow throwing through the cracks, and it's really affected by local weather and surface pollution because of that conduit flow. So for those of you who do not know what stable isotopes are naturally occurring in the environment at a certain percentage. An isotope of each element has the same number of protons for every isotope, but the neutrons differ. So like most oxygens have 8 protons and 8 neutrons, but some oxygens have 8 protons and 9 neutrons, or 8 protons and 10 neutrons. For hydrogen, the stable isotopes are the majority of the hydrogens are 1 proton and 0 neutrons, but there's some stable hydrogen isotopes called deuterium that have 1 proton and 1 neutron. Tritium is a radioactive isotope, so we won't worry about that right now. So since there are different amount of neutrons in each element, or each isotope will have a different mass. So oxygen-16 will be lighter than oxygen-17 or oxygen-18, and hydrogen-1 will be lighter than deuterium. And these masses make a difference in different processes in the environment, as some will prefer taking up the heavier isotope or the lighter isotope, depending on what is going on. So for example, lighter isotopes are preferentially evaporated from a body of water, and the heavier isotopes will stay back at a different fraction. So as I mentioned, stable isotopes are preferentially evaporated in the environment. The lighter isotopes such as oxygen-18 and hydrogen-1 are evaporated easier than deuterium or oxygen-18. So since that's the case, lighter isotopes will be more and more enriched as you go farther and farther from the equator. So as shown on the left map here, there's heavier isotopic compositions near the equator, and as you go farther and farther north or south from the equator, the isotopic composition of oxygen-18 in this instance will be more and more enriched in the lighter isotopes. On the left here, or on the right image here, there's a map of the United States isotopic compositions for deuterium, and in the south here, the isotopic compositions are heavier, and then in the north they're lighter. And it depends on latitude and elevation. So in the Rocky Mountains over here, there's going to be a lot lighter isotopes. And as you can see, these maps aren't very detailed in certain areas, and that's what we tried to figure out in this study, is looking at northeastern Wisconsin and how it varies specifically. So for our study, we examined 97 different wells for deuterium and oxygen-18 isotopic compositions and deuterium excess values in northeastern Wisconsin. There were multiple different collectors over a time span from 2012 to 2020. We used these values to construct the first regional groundwater isoscape for northeastern Wisconsin, and we compared our results with those of Bowen et al. 2012. They created an isoscape for the entire western side of Michigan and found evidence of recycled lake water infiltrating into the shallow Michigan aquifers. Isoscapes are geographic representations of the spatial variation in the isotopic composition of elements. They are produced through the physical and biological fractionation processes that we talked about earlier. In the Midwest, the predominant method for deuterium and oxygen-18 fractionation is temperature and latitudinal variation, as opposed to the elevation variation like in the Rocky Mountains. Deuterium and oxygen-18 also act in a very predictable way as they plot along the global meteoric waterline shown on the bottom right. Our values shared roughly the same slope as the global meteoric waterline. And shown in the middle image here is the results that we got from the deuterium isotopic compositions. Our values followed the expected trend as we found lighter isotopic values toward the north and heavier values toward the south. When we compared this to Bowen et al. 2012, we noticed that while the values may slightly be shifted, the isotopic composition on both sides of Lake Michigan followed roughly the same latitudinal gradient. We also measured d excess and compared it to Bowen et al. 2012. d excess is a measure of the excess deuterium in the water versus oxygen-18. Oxygen is a much larger atom than hydrogen, and therefore an additional neutron in the hydrogen atom will have a much greater impact on the ratio of fractionation than the oxygen will. Since the ratios of the masses are different, the ratios of fractionation will be different, and d excess is a measure of that. Unlike the deuterium and oxygen-18 isoscapes, the d excess values were strikingly different from Bowen's findings. Bowen concluded that there was up to 30% of water in the aquifers in the northwest and southwest corners of the state that was recycled precipitation from Lake Michigan. This tells us that there is a large amount of lake effect rain and snow. On the other hand, we see no longitudinal variation in our samples. The d excess values we see in Wisconsin are similar to those in eastern Michigan, where lake effect precipitation is no longer detected. Because of this, we conclude that there is no substantial amount of lake effect precipitation from Lake Michigan or any other body of water. In addition to creating a regional groundwater isoscape and comparing our results to Bowen, we found some interesting data points. First, we noticed that there are two wells on the eastern shore of Wisconsin that have very low d excess values and relatively high oxygen and hydrogen isotopic compositions. They're the red dots on the left image here. This indicates that there is some incursion of surface water. We think this is from Lake Michigan, but this would be a great opportunity for future studies to test this hypothesis. Another interesting thing we noticed is the lighter d excess group of wells east of Green Bay. This could be from many different reasons. However, we think that there might be enough evaporation from Green Bay industry exhaust to make a noticeable impact on d excess values immediately east of the concentrated industry. This would be another great opportunity for someone to do further research to see if industry is indeed changing the d excess in groundwater near Green Bay. We would like to thank all the well owners and operators for assistance and permission in sampling wells. We would also like to thank Mark Borkart's team who conducted the Kewaunee County groundwater study, which supplied some of our isotope samples. Thank you for listening to this presentation and hopefully you enjoyed it.